Welcome to the Chapter 5 Part 2 video. This covers Section 2 and Section 3 of Chapter 5. I've shortened both sections and combined them into one lesson. This section will cover proving identities very briefly, and then the sum and difference formulas. So cosine of a difference or sum, sine of a difference or sum, and then putting those together to make tangent of a difference or sum. Why is this important? Proving identities gives you an excellent insight into the way mathematical proofs are constructed. We're getting away from two-column proofs and closer to either algebraic proofs, and then eventually the goal is paragraph proofs, although that's more of a college level or AP level proof. So right now we're focusing more so on just being able to explain yourself, being able to look at things step by step, and getting away from the structured nature of a two-column proof of necessarily knowing how many steps something is going to be. These identities provide clear examples of how different the algebra of functions can be from the algebra of real numbers. We've already seen this with exponents and logarithms, but now we're going to look at this property of functions acting differently than numbers for trigonometric functions. And we'll explain more about that when we get there. So the first thing that we want to do, I want to show you an algebraic identity. So notice this doesn't have any trig functions, just algebra. And what I want to do is take this complex expression with all these x's and say, well, no matter what the x value is, this really just equals 2. And the way we're going to do that is starting with the more complicated side. This is kind of a tip. So we're going to start with the right-hand side, and our goal is to simplify that until we get that the answer is 2. And while we're doing that, we're going to make sure that nothing we are doing is illegal, meaning we're not going to multiply by 0, we're not going to divide by 0, we're not going to take logarithm of a negative number or something like that, okay? So making sure that we're following all of the rules that we've been learning since the beginning of algebra. What can I do to this right side of my equation to simplify? Because I have two fractions and I'm subtracting them, logically, what we should do is combine them, right? But take a second, look at it more closely. If I cross multiply to get a common denominator, that's going to make my numerators very messy. So instead of getting a common denominator, what I'm going to do is factor the numerator. Now, if this is the first time you're seeing one of these proofs, and honestly, the first time that I solved this proof, I probably found an LCD. And then I got to a point where I was like, wait, this is complicated. Okay, so I'm going to save you that headache, and I'm going to say LCD will be messy. So instead, let's try simplifying by factoring. So we have x squared minus 1 divided by x minus 1 minus x squared minus 1 divided by x plus 1. If you're ever stuck and you tried something, it didn't work, try rewriting the problem, because probably as you were writing that, you said, hold on a second, x squared minus 1 is a difference of perfect squared, and each of those has a factor that's the denominator. And that's exactly what we're going to use. X plus 1 times x minus 1 divided by x minus 1 equals, nope, not equals, minus x plus 1 times x minus 1 divided by x plus 1. No matter what the fraction is, we can reduce. So I can say x minus 1 divided by x minus 1, x plus 1 divided by x plus 1. So now I'm left with x plus 1 minus, make sure you keep your parentheses, those were grouped together in the numerator, x minus 1. If you drop your parentheses here, you will get the wrong answer. And the way you'll know that it's wrong is because you will get something that's not 2. Remember, that's our goal, is to get this equal to 2. So x plus 1, distribute that negative, minus x plus 1. X minus x is 0. So we get 2 equals 2, and then we're done. Okay, I only used algebraic rules in order to simplify this. Okay, so let's take a look at some of the rules that we used and some of the rules that will be helpful for our future proofs. Okay, if you don't know how to start, and again, a lot of these proofs, just like with using trigonometric identities, it's just going to take practice. It's going to take a little bit of grunt work. Try something. If it doesn't work, try something else. Okay, but if you're stuck, if you want kind of a checklist of things that you can try, here's a list. Starting with the more complicated side and simplifying tends to be easier because we have a lot of practice simplifying expressions. If you are working with trigonometric functions and you get stuck, write everything into sine and cosine. All of our 6 basic trigonometric functions can be written in terms of sine and cosine. Then you might be able to see some patterns. Okay, see what you can factor. Factoring means you might be able to reduce. If that doesn't work, try combining fractions with a common denominator. Like we saw in the last example, that's not always going to work. None of these are always going to work. However, it's a good strategy to try. If that doesn't work, try multiplying the denominator by a conjugate. Again, that's as a giant 1. I should put that as a giant 1. And what do I mean by that? Is if I have, let's say, x over x minus the square root of 4, okay, I can't just multiply by x plus the square root of 4 because that would change the value. I have to multiply it by something over itself. And the value of that is 1. That's what a giant 1 is. So a giant 1 is when I multiply by something over itself. Okay, and then the last one, rewrite the fractions into separate fractions. And that's when I have multiple terms in the numerator. So for example, that would be something like x squared minus 4 divided by x. I can write that as x squared over x minus 4 over x. Now in that example, it didn't really help us simplify, but that's an example of what I'm talking about here. Okay, so let's try another one, but this time it has a trigonometric identity in there. Okay, so if I'm looking at these two sides, there's not one that's clearly more complicated than the other. So that first tip of using the more complicated side and simplifying isn't going to help us in this case. It doesn't matter which side we choose. So I'm going to choose arbitrarily the right-hand side. Okay. Now I'm going to take that and I'm going to apply only identities and see if I can get the left-hand side. So I'm going to rewrite it to see if anything stands out. Sine of x divided by 1 minus cosine of x. I have a 1 there, so maybe a Pythagorean identity, but that cosine of x is not squared, and all of our Pythagorean identities use squared. So how can I go from 1 minus cosine x to 1 minus cosine squared x? Because that would equal sine squared. Okay, now I'm very familiar with the identities, so that might not stick out to you at first. But practice with those identities and it will be easier. It'll get easier the more you practice. So what I'm going to do here, in order to go from 1 minus x to 1 minus x squared, I can multiply by the conjugate. So I'm going to multiply 1 plus cosine of x under 1 plus cosine of x. And this makes me happy because I see that 1 plus cosine of x in the numerator over here, so that tells me I'm probably on the right track. So now I have sine of x times 1 plus cosine of x divided by, if we FOIL this out, those are conjugates, so I know it will be 1 minus cosine squared x, or 1 squared minus cosine squared x. This is where our identities come in. I have that 1 and the cosine squared. The identity that uses both 1 and cosine squared is sine squared x plus cosine squared x equals 1. Subtracting cosine squared from both sides, we get that sine squared x equals 1 minus cosine squared x. This is our favorite Pythagorean identity, number 1. So now we have sine of x times 1 plus cosine of x divided by replacing that whole denominator with sine squared of x. And now I have sine of x divided by sine squared, so I can reduce that to 1 plus cosine of x divided by sine of x. I need these to be identical. So I have 1 plus cosine of x divided by sine of x. They are identical, so my work is done. If I had instead cosine of x plus 1 divided by sine of x, I would have to do the extra step to write it identically to the right-hand side. Just like in geometry, right? In geometry, when you're doing a proof, if you're doing a 2-column proof, that last line needs to be identical to what you wanted to prove. Okay, we didn't have that in this case. So that is an example of a proof with trigonometric identities. Okay, formulas. We learned a lot of different identities in our last video. This time, we're looking at identities as formulas. And that means if I need to calculate sine, cosine, or tangent of an angle that is not on the unit circle, and I want to use unit circle values. Okay, so I'm going to use this formula to find a way to make the angle that I want out of unit circle values. Okay, this will give us exact values, whereas on a calculator, you can approximate these values, but you won't be able to find the exact value. Okay, so these formulas, it's really memorization, but you'll always have access to them. Add them to your formula sheet, and then I'm going to show you kind of a couple tricks. So for sum and difference of sine, we have here sine, and the first thing is sine. For sum and difference of cosine, the first thing we have is cosine. Okay. The next thing that I use to help me remember this, and of course, there are so many of these that, just like with the unit circle, if my methods of how I remember this don't help you, if you do like a Google search or you look at Khan Academy to get more tips and tricks, there are plenty of them out there. When you're signing a mortgage, if you're buying a house or something, or buying a car, or for a loan, sometimes you need to cosine, like 2 signatures. That's how I remember that cosine sticks together. The 2 cosines stick together, and that means that the sines have to stick together, which means the opposite for sum or difference of sine. So sine splits up and cosine splits up. Now, in both of these cases, one argument has u and the other one has v. And then they switch. So that the opposite has u and the opposite has v. Now for cosine, it doesn't matter if they switch or not because of commutative property. So when I'm writing these, a lot of times I'll write it as sine of v times sine of u, just for that consistency. Okay, so that's sine and cosine. There's more tips and tricks. The one that's really important that is almost always forgotten, the ones that I mentioned a lot of times are easier to keep in your head than switching the plus or minus. So again, cosine, the cosines stayed together, so something else switches, and that is the plus or minus. So for cosine, if I have cosine of a sum, it turns into a difference. If I have cosine of a difference, it turns into a sum. Whereas for sine, the sine and cosine's already switched, so the plus or minus stays the same. Okay, this chapter is really difficult for me because I'm trying to say sine and sine. So I try to use, instead of using the word sine to mean positive and negative, I try to use the words positive and negative, but there's just so many times that I'm going to say it that I will forget. So if I'm ever unclear about something, please make sure to ask in class. Okay. For tangent, all we're doing is tangent is sine divided by cosine. So we're taking the formula for sine of a sum or difference and dividing it by the formula for cosine of a sum or difference. But then we can use all of those proofs that we just saw, and we can try simplifying this left-hand side. And what we end up with is this nice kind of version of tangent in terms of tangent. Okay, so make sure you put these on your formula sheet. They're also on the last slide of this presentation that I will post on Blackboard when we finish the chapter. Okay, so let's see if we can apply it. So we want to find the exact value of cosine of 75 degrees. 75 degrees is not on our unit circle. So I need to find out, is there a way to express this as a sum or a difference? So we're going to find cosine of 75 degrees equals cosine of something plus or minus something. 75 is really close to 90. So I could do 90 minus, to get 75, it'd be 90 minus 15. 15 is not on the unit circle, so that didn't work. So let's try something else. Cosine of 75, so 75 can be written as 45 plus 30. Those are both unit circle angles, so we'll do 45 plus 30, and those are in degrees. So notice I took 75 and I kind of guess and checked until I found two unit circle angles that add or subtract to 75. Okay. Now, just because 90 minus 15 didn't work doesn't mean that there's not a difference that would work. As a matter of fact, there should be a difference that would work, but just try to use angles in quadrant 1 as much as you can, because that will make sure that you're not forgetting plus or minuses, because all of the trig functions in quadrant 1 are positive. Okay, so cosine of 45 degrees plus 30 degrees, all in the argument, becomes cosine. I need to cosine with someone. That means my cosines are together. If those are together, then the sign, the operation has to switch. So plus becomes a minus, and that leaves my sines together. And then I fill in the angles. So that's 45 degrees, 30 degrees, 30 degrees, 45 degrees. And again, the last two, you can put them in either order because you're multiplying them. So 5 times 3 is 15, 3 times 5 is 15. Same thing works for sine. As long as they're being multiplied, the commutative property holds. Cosine of 45 degrees, if I wanted to sketch a quick unit circle, I can say 45 degrees is the one in the middle. That's square root of 2 over 2. Cosine of 30 degrees, that's this angle down here. So the x value is square root of 3/2. You should be able to do it this quickly. Sine of 30 degrees, that's the y value, so that's 1/2. Sine of 45 degrees, that's the y value, is square root of 2 over 2. So that was my quick unit circle sketch. Then I have the square root of 2 times the square root of 3 is the square root of 6. minus 1 times the square root of 2 gives me the square root of 6 minus the square root of 2 all over 2. I can't simplify that anymore because the square root of 6 and the square root of 2 are not like radicals. So that is my final answer. If you put that into your calculator, you will get a decimal approximation. And then if you type into your calculator cosine of 75 and you're in degree modes, you will get approximately the same decimal, the same answer. Okay. Let's look at another example. This time we're working backwards. I have an equation and I want to rewrite this as a single trigonometric expression. I want to write it as sine or cosine of a given angle. So the first thing that I'm going to notice, my cosines are not together. I didn't need to cosine for this. So that means this is a sine formula. Sine, the sine and cosine didn't switch, so that means the operation, or the sine and cosine switch, so the operation does not. So that means it's going to be a plus. And then I take my two angles, pi over 3 and pi over 4. So I'm using that formula backwards. Okay, and then I want to find what is pi over 3 plus pi over 4. That means I need to find a least common denominator. So that becomes sine of 4 pi over 12 plus 3 pi over 12. Should I draw in this step? Times 3 over 3 times 4 over 4. That gives me sine of 7 pi 12ths. That is not a unit circle angle, and that is why we would need the formula to solve it. Okay, notice it didn't ask us to solve the value. It said to find the expression as sine or cosine of an angle. Okay, if you have any questions on this section, please reach out to me by email. We will have a chance to practice this together and to work on the Math Excel. And then I'll be available in class this week to answer any questions that you have as well.